In this video, we're wrapping up this chapter with a summary of SN2 and SN1 and a quick look at some nucleophilic substitution reactions in biological systems. Keep in mind, nucleophilic substitution is just one type of reaction that alkyl halides will undergo. There are many other reactions that we will be looking at in later chapters. So for a general substitution reaction, now I used a negatively charged nucleophile, but keep in mind our nucleophiles are not always negative. But in general, if we think about the relative rate, focusing on our alkyl halide, tertiary react faster than secondary, which react faster than methyl, which react faster than primary. And the reason for this unusual trend is because these will undergo SN1, whereas these will undergo SN2. So for an SN2 reaction, the rate law says that the rate is equal to the rate constant K times the concentration of Rx times the concentration of the nucleophile. For SN1, the rate law tells us that the rate is equal to K times the concentration of Rx, not the nucleophile. In terms of the mechanism, here we have our nucleophile reacting with our substrate. As this adds, this is kicked off all at the same time. For an SN1, our RLG leaving group leaves, giving us a carbocation, and then the nucleophile will add. In terms of stereochemistry, an SN2 reaction, because all this happens at the same time, the nucleophile has to add to the face opposite the leaving group, and therefore we get complete inversion of configuration. In the case of an SN1, we have our carbocation intermediate, which is trigonal planar, but the leaving group can still get in the way. Because the carbocation is planar, we're going to get some racemization resulting from the nucleophile adding to either face of the carbocation, but because the leaving group can still be in the way, we will get an excess of inversion. For SN2 reactions, the nucleophile is in the rate law, and so the nucleophile can greatly influence the rate of the reaction. So both the concentration of the nucleophile will make a difference, and the identity of the nucleophile will also make a difference. The better nucleophile leads to the faster reaction, and there are many different characteristics that we need to pay attention to for considering the nucleophilicity. In an SN1 reaction, the nucleophile has no effect except as solvent. For an SN2 reaction, we want a polar aprotic solvent. For an SN1 reaction, we also want a polar solvent. Higher dielectric constant means a faster reaction. And then finally, who undergoes these different reactions? SN2 will be the pathway followed by methyl, primary, and some secondary, whereas SN1 will be the pathway followed by tertiary and some secondary. Now, what is the difference then for the secondary alkyl halides or other secondary substrates with different leaving groups? If we have a weak anionic base or nucleophile, then we are going to get SN2. So a weak anionic base, this could be something like HS-, cyanides, CN-, azide, N3-. These are a few examples of relatively weak bases which will carry out SN2 substitution on a secondary alkyl halide or other secondary substrate. If we have a stronger base, such as an alkoxide, this is too strong, And this is not going to give SN2, it's going to give another mechanism that we're going to look at next chapter. If we have a very, very weak nucleophile, so basically if we're using the solvent, then we can get an SN1 reaction to occur. So here we might be using water or an alcohol or an acid. Any of these would allow solvolysis to occur, and that would give us the product by SN1 mechanism, so proceeding through a carbocation. Now, substitution is also a very important reaction in biological systems. So norepinephrine can be converted to epinephrine, also known as adrenaline, by a nucleophilic substitution reaction. And so here we have S-adenosyl methionine, or SAM, and this is S-adenosyl homocysteine. What we have here is this nitrogen acting as the nucleophile, and this is the R group, which means this entire thing is the leaving group. So the nitrogen forms a new bond with the carbon of the methyl group, and then these electrons move back onto the sulfur. There's another lone pair on here, and this whole thing is the leaving group. S-adenosyl methionine is responsible for methylating many different compounds in biological pathways. So here we are just looking at an SN2 substitution. Now, there are also a lot of really cool substitution reactions, as well as eliminations and others, that happen in the biosynthesis of fatty acids, of terpenoids. And here we have some examples. Terpenoids are compounds that have this carbon skeleton, and isopentyl diphosphate, this is called the biological isoprene units. And so two of these combine to give a 10 carbon terpene. Then we can have a total of 20 carbon terpenes, 30 carbon terpenes. And many of these have important biological functions. Many of them could be essential oils of different spices. And so they are compounds that you definitely have been exposed to, that you have experienced. Looking at the biosynthesis. So we're starting out with dimethylallyl diphosphate, and this is a leaving group. And so the whole diphosphate leaves, and we get this carbocation. Now, this primary carbocation is also, this is called allylic, and it is stabilized by resonance. Now, from this carbocation, isopentenyl diphosphate, this acts as a nucleophile, and it shares its electrons here. So this piece is this piece, and now this is what added here. An elimination reaction happens and we get another alkene, but then this starts over with another SN1 reaction. So the pyrophosphate leaves and we get another carbocation, and it's possible for another IPP, isopentenyl diphosphate, to add, and then we go from a 10 carbon to a 15 carbon to a 20 carbon. Or if water adds, we get to this protonated alcohol, and then after proton transfer, we get to this alcohol. And so this is the result of two SN1 substitutions, along with some other reactions. Geraniol is an essential oil that is responsible for the lovely fragrance of roses. So, in case you were feeling frustrated about all of these substitution reactions, why do I have to learn these substitution reactions? Just keep in mind that Mother Nature loves substitution, and so you should too.